The tube to retainer bar wear, I've talked about that quite a bit. 4 of those were above 35%, but we preventively plugged another 100, and this is unit 2 I'm talking about, 182 tubes just to take them out of service to ensure that that retainer bar problem did not affect the tubes. The tube to tube wear, in unit 2 we found 2 tubes, most likely caused by this in-plane vibration which manifested itself severely in unit 3. So we treated it as such. It was measured at 14% with the probes. It is probably a little less than that. That's a conservative sizing of that. It is well below the 35% limit, but again, not acceptable to keep in service, so they have been plugged. Additionally, and when I talk about the corrective actions later, we identified 321 other tubes between the 2 unit 2 steam generators to preventively plug.
Hey, Tom, just clarify for me, you said, okay, so the 2 tubes, 14% wear at the realm of detectability, but unacceptable to keep those tubes. So what makes that unacceptable?
Because if they're due to tube wear, our experience out of Unit 3 and all of our work through the last 8 months shows the phenomenon in Unit 3 is unpredictable and it's rapid. So to contrast it, for people who are uninformed on the program, a 35% plugging limit, one of the things it's predicated on, if there is a wear indication below 35%, you can, as long as you can predict wear rates, you can justify leaving it in service and operating another cycle or till your next inspection. But it's got to be predictable, you've got to have data, and it's got to be a phenomenon you understand and can predict. Tube-to-tube wear does not fall into that category. The 321 tubes we conservatively plugged between the 2 steam generators. We identified if the plant were to operate at 100% power, based on what we learned out of Unit 3, these would be susceptible potentially to the same phenomena occurring in this fluid elastic instability and excessive vibration, so we plugged them.
Okay. Tom, could you compare and contrast what you plugged in Unit 2 preventively versus Unit 3? Are they the same tubes? Is it a subset of the?
It's a very similar set of tubes. And if you hold that question, Mr. Howell, I'm going to get to a tube map in a few minutes and I can come back to that. So, now Unit 3. So I've kind of talked about Unit 2 and I've introduced Unit 3 quite a bit into it, but let me recap Unit 3. So after the January 31st shutdown, we went in and you start with which tube leaks. So we've got capability, once we shut down and cool down the unit and get into the inspection, to identify the leaking tube. We identified that readily. We then did the complete 100% inspection. The eddy current bobbin coil, the rotating coil examinations. That's done first of all with the leaking tube and the adjacent tubes to confirm the leak and characterize the nature of the leak. Then we did 100% full length of all tubes, just as we would have at the end of the cycle. Unit 3 had only run 11 months, nominally half of the full cycle. We did think of the U-bend portion of those tubes I talked about. We did a full U-bend exam around the retainer bars. Based on what we learned out of Unit 2 on the retainer bar vibration, we went and looked for the same issue in Unit 3, and we did confirm the same design problem with the retainer bar vibration. We then also did visual inspections from the secondary side, and we did specialty eddy current and ultrasonic examinations from inside the tubes to further gather data and understand principally the tube-to-tube wear phenomena, the nature of the wear, and the interaction with the tubes and the support structure. So steam generator inspection results. Stark contrast here. Unit 3 did not meet the inspection program, the performance requirements. As again, it's a backward look at the 11 months of operation. The tube leak itself, as well as the number of issues we found with tube-to-tube wear, did not meet the tech spec program requirements. So Unit 3 starts off very different than Unit 2 by the nature of the tube leak and by the nature of the tube-to-tube wear. Secondly, I described to you the one pressure test we did in Unit 2. One tube related to a retainer bar issue. Test in Unit 2 was done and passed. Unit 3, we had to do 129 tube tests, which is an extremely high number for any unit in an outage, and we had 8 tubes that did not pass. So they failed. So that tells us those 8 tubes would have failed structural integrity requirements. And there are 3 plateaus. One is an operational pressure, one is a main steam line brake accident pressure, and one is an overall structural integrity. 3 failed at the main steam line brake accident pressure, and the remaining 5 at the upper limit of structural integrity.
It might be useful at this point. We have one tube in Unit 2, one of the steam generators that had to be pressure tested, and 129 total between the two generators in Unit 3. Can you just talk briefly about how it is determined to pressure test the tube?
Certainly, Mr. Lamb. And I alluded to this earlier, but basically when you do an examination of tubes with our electrical equipment, our eddy current equipment, and our various probes, and you see some sort of wear indication or flaw in a tube, you've got to characterize it, because it could be a challenge to steam generator tube integrity. It could be, a challenge from a leakage or an integrity issue. So we've got to characterize the flaw and decide, does it have to be plugged, does it hit the 35% limit, or is it closed? And whether it's above or below, we've got to characterize it and conclude that it meets the integrity requirement. If we cannot conclude that based on the shape and size of the flaw and do that analytically, we have to pressure test it. So in Unit 2, we only had one flaw that we felt we had to pressure test to conclusively demonstrate. In Unit 3, we had 129 tubes. We were not satisfied that analytically we could show they met the requirements, so we tested. And in fact, 8 failed. We actually predicted those 8. Based on our calculations and flaw size, we said we would predict this would fail, and those 8 were in fact predicted to fail. So, quick summary, and I'm not going to dwell a lot on Unit 3. We've covered a lot of this. We did see wear at the anti-vibration bars. We saw wear tube support plates similar to Unit 2. We saw the same retainer bar wear, and we saw significant free-span tube-to-tube wear. I will mention, we see a difference in Unit 3 and Unit 2. Unit 3 ran 11 months, and even in the anti-vibration bar tube support wear, what I characterize maybe as normal wear, only to a much greater degree than expected in Unit 2, Unit 3 had even more wear in half the operating time. So Unit 3 is behaving differently than Unit 2, that is clear. And the free-span tube-to-tube wear is very dramatic, but even as we look at our other wear indications, we see a difference between Unit 3 and Unit 2. Very quickly, because I want to get on really to the cause and the actions, to summarize the tube wear retainer bars, we did the same thing we did in Unit 2. We understand that. All those tubes that are affected or potentially affected have been plugged. We did plug 3 tubes above the 35% limit at the anti-vibration bars. Significantly, we plugged 230 tubes above the limit at tube-to-tube support plate. Those are all related to tube-to-tube wear. What is happening there is those tubes that are vibrating excessively, we not only see it in the U-bend area, but they are vibrating against their tube support plates in the straight sections, and that's where that unusually high number comes from compared to Unit 2. And then tube-to-tube wear, 326 tubes between the 2 steam generators. So each Unit 3 steam generator has nominally 10,000 tubes. There's about 160 tubes in each that are affected by this excessive vibration, this excessive movement, the tube-to-tube wear, the tube-to-tube support plate wear, 326. And then we plugged another 292 tubes that would be susceptible at 100% power. Mr. Howell, I think this gets to the comparison you had asked about.
So, plugged roughly 200 more tubes in Unit 3 than in Unit 2.
Anticipating you might ask the question, we've done the math. And in Unit 2, we plugged a total of 517 tubes, either due to indications or preventatively as a conservative measure to add safety margin. In Unit 3, we've plugged 807 tubes. Now, I want everybody to know we are not done with Unit 3. We've done enough work on Unit 3 to understand the effect on Unit 2, and that's where our efforts have been focused. So I'm not going to tell you tonight that I'm done with Unit 3 and 800 tubes.
Hey Tom, one quick question. So 326 tubes plugged due to tube-to-tube wear, and precautionarily 292 more in Unit 3.
In Unit 3, that's right.
Now those 326, did they exceed the 35% value that are required, or that's just?
Some of them did, some of them did not. And I can give you a more detailed breakdown. If you look at the 230 tubes, they're a subset of that 326.
That was going to be my next question.
Those did exceed the 35% at the tube support plate levels.
Yeah, that's going to be my next question, is how the tube wear at the tube support plates was related to the tube-to-tube wear, if they were the same tubes, different tubes.
Those 230 are a subset of 326, and what is happening is those 326 are vibrating excessively, And we're seeing the indications of that in the straight portions against the tube
And
support.
so my follow-up question then would be for the 2 tubes on unit 2 that you characterize as having potential tube-to-tube wear, was there any indication of tube support plate on those 2 tubes that was wear that was a little more than what you saw?
I will
in
have
other
to
tubes?
check the data. We inspected that, but out of the 20,000 tubes in unit 2, those were probably the only 2 I didn't remember. So let me check that data and get back.
We do know that there weren't any, there were no tubes on unit 2 that saw anywhere at the tube support plates which required plugging.
Right.
Right.
We do expect to see some amount of what Tom has characterized as random wear driven by turbulence and normal vibration of the steam generators, but we can follow up with you, Mr. Vance, get you the specifics on those 2 tubes.
We have got all that data.
And just for Mr. Howell's question, you had asked how does the overlay essentially of the unit 2 preventive plugging compared to the unit 3 tubes where we saw tube-to-tube wear? It was our intention to plug a very, very similar area on unit 2, anticipating and with our conclusion that unit 2 could be susceptible to the same phenomenon as unit 3. So our intention was to overlay. When Tom gets to his tube maps here in just a minute, you'll see that there is a specific localized region of the steam generators where we have that concern.
And the material we submitted is with the Cal response. We submitted a lot of material that prevented plugging and the rationale for it and the location is fully described. And again, we'll be glad to get in that in more depth.
So just so I'm clear, Mr. Dietrich, Mr. Polzano, you had roughly 620 tubes that were plugged in unit 3 because of tube-to-tube wear. So either preventively or because they were affected.
That's correct.
And in unit 2, you preventively plugged 321 tubes. The difference being approximately 300 tubes.
That is correct.
And you say in the Cal response it provides the technical basis for that difference.
That's right.
Okay,
Yeah.
that's correct.
We identified a criteria, and it's summarized well in detail in the Cal response. In looking at unit 2, if the plant were at 100% power, the tubes that would be susceptible to fluid elastic instability and this excessive vibration. And we elected to preventively plug all of those susceptible tubes. And we have our criteria laid out. And again, it's deeper than we're prepared to go in tonight, but we can easily take the staff through that. Okay, now with that background on inspection results and kind of a summary of the plugging, I want to talk about tube-to-tube wear. So part of the methodology, if you think back to my earlier comments, so we've identified we've got this tube-to-tube wear occurring in unit 3. So now what is physically happening and why is it happening? Steam generator cutaway, just to refresh us, we're going to be focused mainly on the upper part of the bundle, what we call the U-bend. I've annotated this as area of tube-to-tube wear. And think, one tube comes up in a U shape and comes out on the other side, hot leg to cold leg. So I'm going to show you a picture in a minute that talks about how these tubes are actually moving. Now this graphic, and I've exaggerated the tube, but this gives you a feel for how one of those long tubes, realize the very highest tube, 76 feet long. Inlet to outlet. So this is a long, thin, very strong tube, but it's flexible. Okay? So the blue shape there would show you a tube, say, in a normal condition, with no movement, no deformation. The red shows you this fluid elastic, the effect of this fluid elastic instability causing an in-plane vibration, causing this tube to move excessively, to vibrate excessively. So in this one, you can see what would be on the right side of the screen. The tube flexes or moves to the right as part of the vibration, and you can picture there are tubes above and below it. So you can picture this, if it moves far enough, it's going to contact the tube above it. And on the other side, it's contacting the tube below it. And then when that tube vibrates and flexes back the other way, picture that tube just vibrating back and forth. It's contacting tubes above over here, above on this side, and below on both sides. That is physically what's happening with the tube. So we plotted all of our indications out of the unit 3 steam generators. And what we see here, this is just a schematic, I should just orient you. You're looking at a simple schematic of a cross-section of a steam generator. When you see things like O3H, O3C, O4, these are the tube support plates. So the tubes are straight in this portion. These are the tube support plates that provide horizontal support. Then the tube, if this were a tube, it bends through the U-bend portion, and these V-shaped things are the anti-vibration bars. So what is happening when these tubes flex back and forth, we are seeing the predominant number of these long wear scars due to tube-to-tube contact in this region of the U-bend and in this region. So going back to the previous slide, if the tube is moving back and forth this way, where would I expect to see the contact and the damage? And in fact, this correlates very well with where we are measuring the contact and the damage through all of our tube inspections. So this is part of the story now confirming, we understand how the tube is moving. It correlates with the actual measured damage that we see on the adjacent tubes in the steam generator. When I talk about 326 tubes between the two Unit 2 steam generators, this is where the predominant damage occurs. The other damage I haven't annotated would be those 230 things, whereas the tube vibrates, the top of the tube's moving, well, the straight portion is vibrating as well, and it's impacting the tube support plates. That's where those indications come from. Now, what I want to show you here, and this we'll start talking about an overlay. This is interesting. This is a little hard to understand, but this is actually a picture. We call it a tube map. This is a representation of the 10,000 tubes in one steam generator. So we're kind of in the primary side of the steam generator looking up at what's called the tube sheet, where all the tubes, either the opening is or the outlet is, the inlet or the outlet. And what this testing has shown, this darkened region is where, let's take, this is 3 Echo 88, I believe the number was 161 tubes affected by tube-to-tube wear. They are all clustered in a very tight cluster. So it's a very tight subset of tubes.
I just want to clarify, you said this was the whole steam generator. Looks like it represents half the steam generator. So it's like a hot leg side.
You're looking at the hot leg side. Remember, the tube is a U-bend, so you're seeing the inlet to all 10,000 tubes. I have a companion picture that will show you the cold leg or outlet side. So this does represent all the tubes in a steam generator. It's just a certain view.
I see. Okay, thank you.
Now, Unit 3, Echo 89 steam generator, very similar. Very similar in terms of pattern and very similar in terms of location. So, and what's important here is we understand the cluster, the pattern, and the location. This gives us clues to the conditions that are occurring that affect tubes in that region of the steam generator. We're going to get to the thermal hydraulic conditions in a minute. Now, Unit 2. 2 tubes in Unit 2 between 2 steam generators. That is a picture of the 2 tubes with potential tube-to-tube wear in the number 2 Echo 89 steam generator. Similar location, which led to our conservative decision to treat them as if Unit 2 was showing the early signs of phenomena at 100% power. And that, the clean picture, is the Unit 2 Echo 88 steam generator. We have seen no indication after multiple examinations in 2 Echo 88. But again, from a conservative standpoint and a safety margin standpoint, we feel it is important to treat Unit 2 as susceptible and propose the corrective actions we're proposing. Just going to give you a quick summary. We've talked about a lot of this. Unit 3 first, the number of tube-to-tube wear indications. Now, indications are different than the number of tubes. I can have multiple indications in one tube. Remember, I can have indications on either side of the U-bend. So one tube can have multiple indications. So in Unit 3, I have a total of 823 indications of tube-to-tube wear. They affect 326 tubes. The max depth is 100%. This, in fact, caused the leak. And we have a number of tubes that are well over 50% through wall, or tube-to-tube wear through wall depth. The longest length is 41 inches. That is an extremely long wear mark. Usually wear marks through normal random vibration are limited to the width of the anti-vibration bar that the tube's in contact with. These are extremely long. We had to do 129 pressure tests. That is an unusually high number for any site. We failed 8 pressure tests. That is an unusually high number. And the unit operated only 11 months on brand new steam generators. Unit 2 is clearly different based on results. We had 2 tubes with potential tube-to-tube wear indications. With 2 indications, 2 tubes. The maximum depth is about 14%, was about the limit of detectability. The max length appears to be 6 inches based on our ability to characterize it. We had to do no pressure tests due to tube-to-tube wear, set aside the retainer bar issue. And we failed no pressure test and operated a full cycle of 21 months. So, based on all the work we've done, starting with What was the tube wear? What did it look like? Where did it occur? How does the tube have to move? And with all the expertise we assembled to review this and develop this, we've identified the fluid elastic instability caused excessive tube vibration, and I didn't put up there, but an in-plane direction, which is the unique phenomena that we've seen now in these steam generators in Unit 3. And that occurs when a tube is subject to fluid velocities above a critical value. In other words, the flow of water and steam past the tube is high enough, it's above a critical velocity that will start the tube to vibrate. And secondly, the support structure and the fluid is not damping the tube enough, so the tube vibrates unstably and with a high amplitude and allows it to contact. That is the technical cause of the tube-to-tube flow. 2 key points, because these are important corrective actions. It starts with adverse thermal hydraulic conditions. When you have high fluid velocity, that's what transfers energy to the tube. And that's where it's random, whether it's random vibration or this unique in-plane vibration, energy is transferred to the tube by the fluid. High localized void fraction. What does that mean? When I talk about void fraction or steam quality, I'm talking about how dry the steam is. You know, the function of the steam generator is to boil water, turn it to steam, and turn it to turbine. And you want steam, but all that equipment at the top of the steam generator called moisture separators and steam dryers, because we want a certain amount of steam generated, but we don't want patches of very dry steam. We want to strip the moisture out at the very top of the steam generator. What's happening here, because of the adverse thermal hydraulics, we have high velocities, we also have localized patches of very dry steam. When you have very dry steam, the tubes are not effectively damped by movement through a water fluid, and there's not a water film between the tube and the anti-vibration bar. And that water film actually, the technical term through all the research is squeeze film damping. That water film actually helps to dampen the tube and prevent the vibration. When you have these adverse thermal hydraulics, the tube's excited and the vibration is not dampened. The other piece of this is the support structure, and this gets to a key difference between Unit 2 and Unit 3. Again, up until now, by the other manufacturers and MHI, MHI has been successful with this type of design in smaller steam generators before. The anti-vibration bars have been effective in controlling both out-of-plane and in-plane vibration previously, in MHI's experience and other vendors' experience. With this size steam generator, for whatever reason, this anti-vibration bar design was not effective, coupled with the adverse thermal hydraulics. So when the two combine, we have this localized area where this subset of tubes, nominally 160 tubes out of 10,000 in steam generators, were exposed to this and vibrated excessively, causing the damage.
And Tom, you said MHI was successful with the previous generators, a similar anti-vibration design. Would it be fair to say that potentially those other generators just weren't challenged so much in the design because the thermohydraulic conditions were not the same?
It's hard to make a conclusive statement. We've done enough work with MHI and the other vendors. And MHI has supplied similar steam generators in Japan, elsewhere internationally, and one other set in the U.S., and they have been small. So it would appear to us that our thermal hydraulics, our fluid velocities and void fractions at 100% power, and that's the key, are higher than they have previously experienced before in their design.
Okay.
Mr. Hall?
Yeah, I just need a second to organize my thoughts. So, MHI, the vendor, when they designed the anti-vibration bars for their steam generators, it represented a departure from their previous design philosophy. In fact, they were trying to maximize damping and minimize contact force, right? But I guess they didn't recognize, or it was not recognized, that by doing so, that lowered the natural frequency of the tubes in the in-plane direction. Is that fair to say?
I won't say that conclusively without talking to MHI. I understand what you're saying. They have previously used this anti-vibration bar design specifically at the plant in this country, much smaller plant. They've used it elsewhere. In terms of their design philosophy, the zero gap, the contact force, without consulting with MHI, I can't state conclusively that that was their goal.
Okay. Clearly, it was Edison's goal to minimize dings and dents in those tubes from the contact of the anti-vibration bars with the tubes.
Our goal, our specification was a steam generator that would operate 40 years, very little tube wear, no tube leaks for a number of years, etc. In terms of how the designer does that to achieve those goals, we provide oversight, we rely on their judgment, their engineering expertise, and our oversight.
Hey, Tom, just to, Mr. Howell, to address your question, this goes back to some elements of what we were seeking in our replacement steam generators. The reason the industry, as you gentlemen know, the reason the industry has gone through a extensive and expensive and prolonged process of replacing steam generators was primarily due to phenomena that occurred in the course of the lives of those steam generators that weren't fully expected when the steam generators were installed back in the original construction, the 60s, 70s, into the 80s for us. That was primarily involved cracking of the tubes, which was driven by a chemical corrosive attack. But also, one thing that's important, very important to note and to understand, is that at San Onofre, we were also seeing on the original steam generators a significant amount of wear. Not just the cracking, but we were seeing a significant amount of wear. And on one of the units, I recall being Unit 2, the steam generators were actually approaching the end of their useful life because of the tube plugging that we were having to do due to wear on the tubes, not just the cracking. So in our replacement steam generator design and specification, our intention was to minimize wear because that was in fact what had driven us to the replacement requirement, and in our desire to install components that we knew could operate reliably for the operating life of the plants and be able to safely, correctly, efficiently provide electric service to our customers and ratepayers. We were seeking to resolve the issues that were requiring us to replace the steam generator. So our desire was to minimize wear. We also addressed the generic or general industry issue of the cracking, and that came through the replacement of the tube material, going from what was called alloy 600 Inconel to the alloy 690. So a little bit differently maybe than other steam generator replacements in the industry, which were primarily driven by the corrosion cracking. The San Onofre replacements were driven by wear as well. And so that's why this wear focus in our specification to the steam generator designers is so important to us. Thank you.
Okay. So just to recap, in accordance with the confirmatory action letter commitments we made, we've identified the cause of the tube-to-tube contact and wear in Unit 3. That was one of the key commitments in the confirmatory action letter. We understand what has occurred, fluid elastic instability, excessive vibration, and we understand what causes it in terms of adverse thermal hydraulics and the support structure. And then I'm going to move on to our corrective actions for Unit 2. Mr. Lang?
I keep hitting the button. Go ahead, Art.
Well, when you say support structure, you mean because there's a lack of contact between the ABBs and the tubes?
Well, I'm starting with the fact that support structure was ineffective in damping vibration. Whether it was lack of contact or lack of sufficient contact force, some of that is yet to be concluded. Okay, those are some of the early indications that the zero contact design, and in fact, if you think about it, Unit 2 is very different than Unit 3. Unit 2 support structure was much more effective than Unit 3 with the same thermal hydraulics. The thermal hydraulics are the same for all 4 steam generators, yet Unit 3, after only 11 months, has significant damage. Unit 2 maybe has 2 indications.
But the contact force in Unit 2 has been probabilistically estimated to be twice that in Unit 3.
Yes, that's part of the difference. So as we continue to unravel this with MHI and do deeper technical work and causal analysis work, the support structure is more effective in Unit 2. Our testing and MHI's testing, the analysis well of all other experts indicates there is both more contact and contact force between the anti-vibration bars and the tubes in Unit 2 than exists in Unit 3.
So just so we're clear, I think you know where I'm going with this. The point is that these anti-vibration bars were designed purposefully to have zero contact force. And yet now the conclusion is, after the event occurred in the tube leak, that it's because of that lack of contact force that contributed to the phenomenon of fluid elastic instability.
I think that's a fair statement at this point.
Well, I think what's important to point out here, so we help with a little bit more information, and it does get very technical. It's not our intention to to lose people in this discussion, but Tom had previously mentioned, Mr. Howell, the squeeze film damping. And although the steam generators were designed in a hot operating condition, there would be contact, but there wasn't a specific specification for the amount of force that would exist between the anti-vibration bar and the tube. The intention was, and the technical analysis and science behind fluid elastic instability and steam generator design has showed the effectiveness of this squeeze film damping. And so what the design counted on was for there to be a film of water there. And because that film of water was there, it would in itself provide enough resistance in addition to the essentially zero gap, although no force, to provide resistance for the tube moving. And those are the things that we could continue to study in our root cause. What is very important to point out, and I don't mean to jump ahead, but we are talking very specifically about all of these thermohydraulic conditions that exist at 100% power. And this is the fundamental reason that in our proposed confirmatory action letter response, our desire is to only operate the unit at 70% power. And Tom, we have information for you here in a few minutes that will show the improvements in the thermal hydraulic conditions, the fact that you reduce the velocity and you improve the amount of moisture in the steam to restore this squeeze film damping, even on Unit 2, where we didn't see the tube-to-tube work. So I do think we get to this point. There is a tremendous amount of science and research behind fluid elastic instability, as I'm sure you're aware, Mr. Howell. And, we have learned a lot working with the renowned experts in the industry, some of the most published professors and other folks in the world. We look very much forward to that discussion around some of these very specific but important aspects of steam generator design.
I appreciate that, and I know we're jumping ahead. So you talked about how the reduction of power will improve the thermohydraulic conditions. That is one of the big contributors to the fluid elastic instability, but you also talked about the support structure. So as part of the discussion, I imagine you're going to also tell us how that factors into operating, justification for operating 70% power.
Okay, I'll be glad to address that. And that is fully described in our confirmatory action letter response, the role of the support structure. And again, Unit 2 has a more effective support structure than Unit 3.
Yeah, if I could just tack on to that, you keep talking about an adverse thermohydraulic condition, and that is the kind of the precursor that imparts the energy to the tubes to allow an inadequate support structure to allow excessive vibration to occur. My question, you're going to talk about 70% power as a reduction in those thermohydraulic conditions. In your CAL response, do you discuss other factors in the design of these generators that ultimately created this adverse thermohydraulic condition? You're saying it can go away if you go to reduced power, but why is it there in the first place? What aspects of the design created that condition? That's my question.
The current CAL response, and we'll get into this over the next several weeks as we get into the technical detail, describes what occurred. I'm sorry?
Answer the question.
Mic on? Okay. Anyway, the CAL response describes the condition, describes why it occurred, describes the role of the thermal hydraulics and the fact that they were underpredicted, describes the contact force problem that occurred. At that point, MHI's root cause has not been completed, so as we look at longer-term actions, there's more technical work to do to better understand the contact force assumptions, the role of contact force, and whether, in the end, it's the number of tubes in physical space that created the thermal hydraulics, as well as the role of the contact force.
Yeah, I understand. To do a full repair, restore the generators to 100% power,
Right.
You'll have to be able to understand how to bring a thermohydraulic condition back in line with something normal that doesn't create this excessive force on the tubes. But I think it is important to understand what the contributors are so that we can understand how effective the 70% power reduction is.
And I think you'll find in our CAL response, we've discussed the contributors.
I think, John, your next point, we're going to get into the roles of the thermohydraulic code and talk about specifically how the thermohydraulic code and some of the issues associated with the thermohydraulic code factored into this situation. And there is specific information in our confirmatory action letter response which shows the velocities within our steam generators at 100% power, our velocities at 70% power, and experience within the nuclear industry today of similarly designed steam generators at the same velocities that we are proposing in our operation at 70% power. And it shows that those steam generators are stable. Those steam generators don't see this in-plane fluid elastic instability. So certainly more than willing to talk about all aspects.
Yeah, I think, Mr. Dietrich, the reason why we're asking is you all have defined the phenomenon as adverse thermohydraulic conditions and support structure unable to control the resulting vibration.
Correct.
And so part of the, I don't know if it's part or all, of the action that you're using to justify operating 70% power is the actual power reduction, and you're no longer worried about the support structure performing a design function that it was never intended to perform, which is in-plane stability for those tubes. Or we still need to rely on some support in the in-plane direction to prevent FEI occurring.
And we'll address that as we go forward. Let me talk for a minute about the role of the thermohydraulic code. In previous meetings, we've talked about the conclusion that MHI's thermohydraulic code underpredicted the thermohydraulics and effectively showed more margin to the out-of-plane vibration phenomena than actually existed. Just real quickly, the thermohydraulic code, the second block in my little diagram here, I've made a simple diagram. You start with operating conditions. The thermohydraulic code analyzes and models the conditions inside the steam generator the tubes are exposed to. That then feeds both the structural and structural vibration model and tube wear models. So the key here is starting with reasonably accurate thermohydraulic predictions from the code. The code that MHI used, FIT 3, was used in the design of our replacement steam generators back in 2005, 2006. Had been in use for 15 or so years by MHI and their other steam generator designs. And in our case, it underpredicted the critical thermohydraulic conditions, specifically the fluid velocity and the void fraction. We talked earlier, the fluid velocity excites the tubes. The void fraction or steam quality is what helps dampen the movement and helps the support structure be more effective through the squeeze film damping. Because of that underprediction, they didn't recognize the lack of margin to the vibration phenomenon. Today's work, the U.S. industry typically uses a code called AETHOS, which has been around for a number of years, developed by the EPRI group, the Electric Power Research Institute. As we run AETHOS today on the replacement steam generators, it predicts much more adverse thermohydraulic conditions, higher velocities, higher void fractions. All the analysis we've done to support the Unit 2 restart relies on AETHOS, not the FIT 3 code, which was part of the problem that MHI had in their design phase in not recognizing this vulnerability. And we didn't rely just on MHI running AETHOS or Southern California Edison running AETHOS. We've had AETHOS run independently by Areva and Westinghouse, who also design and build steam generators. And we've had Areva run a separate proprietary thermohydraulic code. All of those get very good correlated results with AETHOS today and show more severe conditions than FIT 3 today.
So yes, so AETHOS shows more severe conditions, but the results from AETHOS also ultimately resulted in stability ratios that were satisfactory. Is that not correct?
In MHI's work, it's even using AETHOS predictions today, and the key is assuming the support structure is effective, showed stability ratios just under 1 in some cases, which is acceptable. Okay? Not, the 1.0 would be the cutoff to acceptable or unacceptable. Greater than 1 would be unacceptable. But the key is that assumes the support structure is effective. So clearly, the support structure is a significant element of what did not work effectively in this steam generator design.
So given that, you are going to explain how, at least for reference, that the Cal response addresses the role of either a design change or modifications or other fixes to the support structure to justify operating at 70% power.
The Cal response discusses 70% power showing the thermal hydraulics are acceptable, and in Unit 2 the support structure is acceptable at that lower power level. Again, you have significantly less fluid velocity at 70% compared to 100%. I'll show you a schematic in a minute that shows that. And you have a significantly lower void fraction, which means much better damping by both the fluid and the supports in Unit 2. And the Cal response does address that specifically.
Yeah, it would be helpful if you could address at least an overview of how it is addressed. I mean, I know you can't go into all the details in the operational assessment, but at least you give us a sense, you know, whether this is a calculation methodology, a new methodology.
If you can hold that, let me get through the upcoming slides, and then I'll come back to that question about how we treated the support structure in the operational assessments. Because it was treated explicitly in the operational assessment we did in one case.
Mr. Palmer, I had one other question. You indicated that the Fit 3 has been used by MHL for approximately 15 years, and I assume you mean successfully or
Yes.
by that, but that in underpredicted, in your case, in underpredicted thermal hydraulic conditions. Could you speak to why, in your case, it underpredicted that, or whereas apparently?
For our specific, yes, I can. For our specific case, Fit 3, it just gets fairly detailed. Our replacement steam generators have a triangular two-pitch design. Previous MHI designs that Fit 3 was based on had what's called a square array design. So there's a physical difference in the way the tubes are configured, those 10,000 or so tubes in each steam generator. So Fit 3 had to be modified to model the triangular two-pitch design. There's also under the U.S. ASME, Associated Mechanical Engineers Code, tells you certain dimensions to use in your calculations. Fit 3 did not take those dimensions correctly. And that was not an input error by a person, that was embedded in how the code was built. So Fit 3 had some problems in how they modeled the triangular pitch steam generators and the values that the US ASME code required that resulted in an under-calculation of velocity. So that, in a summary level, is what occurred with Fit 3 that caused the under-prediction.
And had they modeled other steam generators that used a triangular pitch code for pitch as well?
I believe they have. They've originally started with square pitch. I believe they've done other triangular pitch steam generators overseas, but with, quite frankly, smaller steam generators with less severe thermal hydraulics. So I suspect even if an error occurred, it was not a significant contributor to the problem.
Could you describe again when you talk about the ATHOS verification as compared to Fit 3 verification, why this should have more confidence in ATHOS as compared to Fit 3?
Certainly. So first of all, ATHOS was developed by the Electrical Power Research Institute a number of years ago, and a code like that is verified against experimental data. So well beyond our use of San Onofre, the code is written, and then test data is taken off of experimental test loops where they mock up portions of steam generators and actually measure parameters. Then they model that test loop with the code and say, does the code predict with reasonable accuracy what I actually measure? So that's how a code like ATHOS is originally developed and validated. So it's a validated code. What we did is we looked at this problem and said, let's have MHI and us run ATHOS and look at the conditions. And the ATHOS conditions came out more severe than the Fit 3 conditions that were done during the design phase in 2005, 2006. To not just rely on that, we had Arriva run ATHOS, their own version of ATHOS, and confirm the calculations MHI was getting with ATHOS, the more severe calculations. We then had Westinghouse, who has a proprietary version of ATHOS, do that as well. So we've had Arriva and Westinghouse run ATHOS independently from MHI and coming up with similar answers out of the ATHOS code. And Arriva also uses a proprietary code called Kafka. They also ran Kafka and have results in a similar range as ATHOS. So we've done some extensive work here to independently run ATHOS to confirm what MHI's calculations are with ATHOS.
Hey, Tom, just one other, we mentioned the Fit 3 code was modified because of the going from square pitch, which Fit 3 usually used, to triangular pitch. My understanding also is these codes, the ATHOS codes, as well as the MHI, are really based on out-of-plane vibration. They don't really look at in-plane vibration because it's assumed it's not going to occur if out-of-plane is prevented. So that appears, can you explain how the codes had to be modified to model the in-plane vibration?
Yeah, I think what you're talking about, the thermal hydraulics are done independent of what vibration mode you're talking about. So as we talk Fit 3, it calculates velocity, void fractions, hydrodynamic pressure. It is independent of what vibration phenomena. I think what you're talking about is these downstream models that look at the particular vibration modes and then the wear models. Again, up until this point, industry experience, and this is not just MHI, this is the other vendors as well, have basically modeled and analyzed for out-of-plane vibration, and if that was acceptable, their experience was there was significant margin to in-plane vibration and was not explicitly